Entanglement gets called spooky, but inside a quantum chip, it's doing something far more useful than being mysterious. You've probably heard that entanglement means two particles are connected no matter how far apart they are. That's true, but it doesn't explain why engineers actually need it to build a faster computer. Start with a regular bit. It's a 0 or a 1. Full stop. A qubit can be in a mix of both at the same time, which is called superposition. That alone is interesting, but it's not enough. Now imagine two qubits that are entangled. Measuring one instantly tells you something definite about the other. They're correlated in a way that has no classical equivalent. Think of it like this. Flip two ordinary coins, and you get 4 independent outcomes. With two entangled qubits, the outcomes are locked together. Certain combinations are simply ruled out before you even look. Inside a quantum processor, that correlation is a resource. When you entangle many qubits together, you build up a shared quantum state that encodes information across all of them at once. A circuit with 10 entangled qubits can represent 2 to the power of 10. 10 states simultaneously. That's 1,024 states in one snapshot. Add more qubits, and that number explodes. The practical payoff is that certain calculations, like searching a huge database or factoring a large number, can be structured so wrong answers interfere with each other and cancel out, while right answers reinforce. Entanglement is what makes that interference work across multiple qubits at the same time. Without it, each qubit would just be doing its own isolated thing, and you'd lose the advantage entirely. Creating and holding entanglement is genuinely hard. Qubits are fragile. Any stray heat or electromagnetic noise breaks the entangled state in a process called decoherence. That's why quantum processors run near absolute zero, colder than outer space. It's not for show. It's to keep the entangled state stable long enough to actually compute something. Researchers are also working on error correction schemes that use entanglement between extra qubits to detect and fix mistakes without directly measuring the data qubits and collapsing them. So entanglement isn't just a philosophical curiosity about particles far apart. It's the mechanism that lets a quantum computer treat many qubits as one coordinated system instead of a pile of independent switches. The spooky description isn't wrong, it just stops too early. The real story is about correlation as a computational tool, and engineers are still figuring out how far that tool can reach. If you want to go deeper, the next question worth asking is how quantum gates actually create entanglement in the first place. That gets into some genuinely strange territory.